Okay, so let us start the class. So I think my voice is audible and the screen is also visible to you. Yeah, so in the last lecture, we were discussing about interconnect parasitics, and we talked about the how to calculate the resistance also and inductance also, which are actually the parasitics associated with your wire or interconnects, right? Now let us talk about the interconnect modeling, like how we will model an interconnect by using these RLC values. Okay. So I think yesterday itself I mentioned that we will use this approximation, which is called ideal wire approximation. So where we'll consider the whole wire as an equipotential region. That is, at each point on the wire, the potential is same. So that is actually in real world scenario, it is not so. The potential on around the wire, I mean along the points on the wire, so it changes. And as the length of the wire increases, the resistance of the wire also increases, right? So equipotential approximation cannot hold true for long wires. So this one has to keep in mind while modeling the interconnects. Now there are two models which can be utilized for a capacitance of a model, capacitance of a wire. For deciding a capacitance of a wire, two models can be there. One is called lumped model and the other is called distributed model. Okay. So in lumped model, in fact, this one is which is shown over here. This is called distributed wire model. So where the wire capacitance here is distributed along the length of the wire. So the distributed approach means here that the wire capacitance, so that is distributed along the length of the wire, right? So let's say that this is my wire length L, let's say length of the wire, and the wire capacitance is distributed along the length of the wire. That is, let us say that there are n sections of this wire, right? So that means each section is of L by n length, right? So total length is L, and if there are n sections, so L by n is the each segment length. That is, this segment length is L by n, right? So each segment has its own capacitance value, right? So these capacitance are distributed along the wire. Okay. So anyhow, so as I said that in the distributed model, for example, this one, the wire capacitance is distributed along the length of the wire, right? So each segment of this wire has a separate capacitance, right? Now, apart from the distributed model, so this is called a lumped model, this one, the down one, the bottom one. So where all these capacitances are lumped into a single capacitor, right? So this is lumped capacitor based wire model, and this is distributed capacitor based wire model. So distributed capacitance based wire model is more accurate than lumped capacitance based model. But and the calculations, that is, if somebody wants to find out the delay of this lumped capacitor model, so it's a first order circuit, delay can be easily found. But here, since there are many time constants in the distributed model, in fact, if resistances are also here, then you'll have many RCs, that is many time constants in this circuit, and many differential equations will also appear, right? A set of differential equation needs to be solved to find out the delay at the output. So the calculation becomes very complex unless you have some support of SPICE simulations, right? So wire parasitics are here distributed along its length, and they are not lumped into a single position as in this lumped model. Now it is useful to consider the capacitance only model, right? So since here you will see that in this picture, you see that only capacitance is mentioned over here, right? So no resistance is associated with the wire. So this is also an useful approximation, that is to consider only capacitance, and this is only possible when the resistance of the wire is small. So if the resistance of this length of wire is small, then one can ignore resistance, and then only capacitance only model can be there for the interconnector wire. Now if there is no resistance here, so then it obviously means that this entire length of the wire, so this represents actually a load for the driver. Let's say this is my driver here. This is my driver, which is driving another maybe some load inverter, and between these two drivers, I mean these two drivers are connected. I mean this is driver, and let's say this is a load inverter, and both are connected by a wire here. And let's say the resistance of the wire is negligible, so capacitance only model is considered here for the wire. So this wire actually represents a load for this driver. So apart from this load, this wire also appears as a load for this driver. Okay? And there will be no delay from the wire, this wire, because no resistance is, we are considering no resistance since it's a small wire. Capacitance only model has no delay, so it will not represent any delay, but it will represent a load to this driver. Okay. Now this lumped model, where you club all these capacitances into single capacitance, so this is inaccurate approach, and this becomes inaccurate for long interconnect wires, because long interconnect wires, they will also have resistances associated with the wire. As the wire length increases, we understand that the resistance of the wire also increases. So in that case, you will also see resistances over here along the length of the wire, right? So this resistance cannot be ignored. So in this criteria, when the wire is long, this approach, that is lumped model, this will fail. Okay, then one has to utilize this distributed approach for calculating delays. So how the total lump capacitance is calculated? The lumped value of the capacitance, that is this capacitance here, this is calculated by multiplying the length of the wire with C wire, that is capacitance per unit length, right? So all these capacitances are capacitances per unit length, right, in a distributed model. So lumped value of the capacitance is calculated by multiplying the length of the wire, total length of the wire, by the capacitance per unit length, C wire. Now let us take a small exercise, and let us assume that this driver is connected to this interconnect. This interconnect is connected to this driver, and this driver has a series resistance of 10 kilo ohm. Let's say that this driver has a series resistance of 10 kilo ohm. Okay. And this driver, along with series resistance of 10 kilo ohm, is driving this wire, right? This wire, and this wire is 10 centimeter long. So L is 10 centimeter for this wire, and width is 1 mm, and it is a aluminum 1 wire. Okay, and the total value of the lumped capacitor, I mean these capacitances all, when they are clubbed, so total lumped capacitor value is 11 picofarad, right? So I'll write here C lumped of this wire is 11 picofarads. Now one has to find now the output and time for output to reach 50%, okay, and 90% points. Okay. And assume that a transient step input, which is V in, that is going from 0 to V, is applied at the input. So here you have applied a transient input, so which is going from 0 to V as an input. Okay. So we have to find the delay, that is 50% delay and 90% delay. Okay. TP, we used to calculate TPHL and TPLH. Earlier we had calculated, and then we calculated a propagation delay 50% propagation delay and 90% propagation delay. So same we have to calculate here. Okay. So how we will calculate this? So let us try to calculate. So let us first of all try to lump all these values. So this has a resistance of 10. So let's make a circuit which has a resistance Rs. Okay. And then I have all these capacitances of the wire, these capacitances lumped into one value. So it becomes a simple first order RC circuit. Okay. So this is my C lumped here, C lump. Okay. And here maybe I'll apply my input V in. And this is my V out here. So I can make a circuit like this. Right?
Hello, sir.
Yeah, please.
Sir, in what condition we will differentiate that long wire and short wire? Is there any condition, sir?
Yeah, so long wires, the wires which are more than, let's say 1 micrometer. So those are considered, let us say, long wires. Okay? And also, not just long wires, one has to also see what is the delay of this driver. So if the delay of the driver is more than the delay of the wire which is being driven, so then also you can ignore the resistance of the wire. But if the delay of the wire is more than the delay of the driver, so even if now the wire is a short wire, one has to consider resistance because the delay of the wire is now greater than the delay of the driver. So this is one of the approximation one has to utilize. Okay. In fact, when the delay of the wire is greater than the delay of the driver, always one has to use the RC model, not only capacitance model. Capacitance only model can be used in two situations. That is when the length of the wire is long. So length of the wire is long, so that can only be judged by looking at the delay of the driver. So if the delay of the driver gate is smaller, then we'll say that the length is long. So we'll include this R also here. So RC delay of the wire will come into picture. So I hope this is clear.
Yes, sir.
Okay. So let us try to, in fact, this circuit we had seen earlier also. And if we try to calculate V out, okay, at this point, okay, so one can simply find out V out. In fact, one can say that current, in this circuit, so all current one has to, equate to 0, right? So that is current flowing through this resistance and plus current flowing through this lumped capacitor. So that can be equal to 0, right? So that is V in minus V out by RS plus this is C dV out by dV in, right? Current this through this is, that is I through C is C lump dV out by dV in, right? And this can be added to V in minus V out. So this is V in minus V out by RS. Okay. Plus IC. So that is equal to 0, right? So if you do this, you will get this equation here, the same equation here. Simply we have brought now V out, this one. Yeah, both are here now. So you will get this here. And now this can further be, solved. And this can be reduced to this equation. This we had seen earlier. That is V out is 1 minus e to the power minus t by tau into V in. So, yeah, this is V in. And tau is here RC, equal to RC. Okay. Now if we put V out, that is for 50% point, you have to put V out as 0.5 V in, right? So put V out as 0.5 V in and you get the delay is equal to 0.69 RC. Similarly, if you put 0.9 V in for 90%, put V out as 0.9 V in, you will get this delay 90% as 2.2 tau or 2.2 RC. Okay. So R and C are already given to you. 10 kilo ohm is R and 11 picofarad is the lump capacitor value. So if you do this, we'll get 50% delay as 76 nanoseconds and 90% delay as 242 nanoseconds. So this way one can calculate the delay at the output. Yeah. Now imagine, in this situation we had assumed that no resistance, wire has no resistance, right? So imagine if there is a resistance in the wire, right? So maybe let's say I have now the circuit modified as this circuit. Yeah? So I have many time constants, that is RC here in this circuit. Okay. Now for this circuit, the differential equation, right? So you will see that you will have a set of differential equation, not just one differential equation here, right? So here we had just one differential equation because we had first order RC circuit which had only one resistance and one capacitance. But now in this case where you have many RC time constants, so here you will have to solve a set of differential equations and a set of RC time constant. Now the analysis of this circuit, in fact there are no closed form approximations. Closed form solution for this type of problem does not exist. So unless you perform a SPICE simulation, one cannot find out the delay of this circuit. Yeah, the closed form solution for this circuit. So that does not exist. So one has to use either approximate models or SPICE simulations. Now the same circuit can be, delay of the same circuit can be found if one uses this technique which is called Elmore delay formula. By using this Elmore delay method, one can find out the delay of this type of circuit where you have many RC time constants. Okay. So on paper, that is, analysis can be done. So you don't need a SPICE simulation software. So Elmore delay formula can be utilized to find out the delay of this circuit. So what is Elmore delay? So Elmore was again a researcher, and in 1948 he came up with concept of finding out the delay of an RC circuit which has many R's and many C's and many capacitances. Okay. So let us say we have a RC network, a resistance and capacitance network which looks like this. Okay. Or it's a RC tree, we call it, right? Now one important thing you will notice here is that there are no resistive loops in this picture, right? So Elmore delay model is only applicable to networks where there are no resistive loops, okay? And there is a single input node. So this is my input node, root node we call it, or source node. Okay? So source node or root node is input node. So Elmore delay is only applicable to circuits which have no resistive loops and which have only single input node, and all capacitances are between node and ground. So this circuit has been again divided into nodes, like for example node 1. So this is node 2, 3, 4, and let us say node I. So you have capacitance between node and ground, not between a node and another node, or maybe mutual capacitances between these nodes, right? So capacitance is only between node and ground. So then only this Elmore delay model can be applied. Now for Elmore delay model, one has to calculate the path resistance and the shared path resistance. Okay. So what is path resistance? So let us say that one wants to calculate a delay from this root node to node number 4, right? So from root node to node number 4, if somebody wants to calculate the delay. So the path resistance in this case would be R1 plus R4, sorry, R3 plus R4, right? So this is the path resistance, total path resistance from here to here, right? That is delay from root node to node number 4. So the total path resistance will be R1 plus R3 plus R4, and the total shared path resistance. So this will be, that is R1 plus R3. Yeah, so this is the shared path resistance. This is my output node, let us say ith node. So the total shared path resistance between node number 4 and node number I So this is R1 plus R3. So I calculate this shared path resistance here. So let's say I want to calculate the shared path resistance for from root node to ith node and fourth node, right? So shared path resistance from root node to ith node and node number 4 is these two resistances are shared. That is R1 and R3 are shared between node number I and node number 4. So Ri4 I write as R1 plus R3. Similarly, if somebody wants to say that what is the shared path resistance between from root node to ith node and second node, right? Second node is here and ith node is here, right? So the total resistance is only R1. So Ri2 I write as R1. Now the delay, the Elmore delay formula says that the delay at any node or delay at ith node. So ith could be maybe third node, fourth node, or second node, whatever. So the delay at ith node can be calculated by using this formula, that is summation of k's 1 to n ck rik, right? So k is again here, maybe 4 here or maybe 2 here, right? So this way one can find out the delay at any node. So for example, somebody wants to find out the delay at ith node, that is this node, okay, using this formula. So k is 1 to n, right? So this will be R1 C1, okay, then R1 C2 plus R1 plus R3 C3, R1 plus R3 C3. Only shared path resistance will be considered. So when k is equal to 1, for example, when k is equal to 1, so I have R1 C1, okay, RC is R1 C1. So when k is equal to 2, k is equal to 2 here, so the delay would be R1 plus R1 and the shared path resistance. Ri4 is or Rik is shared path resistance. So when k is equal to 2, the total delay, that is RC delay, is R1 C2, because shared path resistance is R1. So R2 is not coming into the picture. Similarly, somebody wants to find out a delay at when k is equal to 3. So k is equal to 3. So k is equal to 3, that means here. So the total delay will be R1 plus R3 into C3, right? So similarly, at the ith node, one can find the delay by extending this formula by simply assuming k is equal to 1 to n. One can find out the delay. So that was the delay for a branched chain. Now one can also find out the delay by using Elmore delay model or method for a RC chain which is non-branched. So here you will see that there are no branches appearing from the nodes. Here we had branches. So but here we don't have any branch. Okay. So again the same formula can be utilized to calculate the delay. So for example, the delay at the second node, this node. So this can be calculated by using the same formula by R1 C1 plus R1 plus R2 C2, right? So delay at second node can be found by using the same old formula. Okay. Similarly, the delay at ith node, okay, so this can be found by using this equation. So this way, Elmore delay model can be utilized to find out delay for circuits which have many time constants and where a set of differential equation appear because of many resistances and many capacitances in the circuit. So in Elmore relay model, we also assume that the total wire length, right? So wire is actually modeled by n equal length segments. That is, total wire is divided into n equal length segments, and length of each segment will be equal to L by n. So that the resistance and capacitance of each segment would be equal to RL by n and CL by n, right? So I have this wire. I'll divide this wire into n number of sections. Okay. Let's say n is this 1, 2, 3, 4, 5, 6. So let's say n is equal to 6 here. So total wire is divided into n number of sections. Okay. And the length of each section, that is, total length was L. So length of each section is L by n. So this is L by N. This is also L by N. Yeah, so all are L by N length. And the resistance and capacitance of each section are RL by N and CL by N. Yeah, R into length of each section, C into length of each section. So the delay, can be calculated by again using the same Elmore delay formula. And this time we will put, so this can be calculated, and this comes out to be equal to this much. RC L square. Simply in the previous formula, here we will utilize C as CL by N and R as RL by N. So C as CL by N and R as RL by N we have to put, and you'll get this formula. And further, if you reduce this, so you'll get this much, RC N plus 1 by 2N. Now if N is very large, okay, so if N is very large here, so this becomes RC by 2. Okay, so if N is large here, N is large here, so these two N cancel, and we have RC by 2. Okay, so the delay becomes equal to RC by 2. Now R is RL by N, this one, and C is CL by N. So put it here. So we get final delay as RC L square by 2. Okay, that is RC.
Sir, how this increasing term will come, sir? RC plus 2, RC plus NRC, sir. This.
Yeah, so here all R and C's are equal.
Yes, sir.
Right. So you will add this, that is from here itself you will see 2R C3. Right. Similarly, 2R C4, 3R C5, and so on. So once you put all these things here in this formula and say that all length of each segment is equal, and the resistances of each segments are also equal, so then they will automatically come RC2, RC3, RC, and NRC. So they will automatically come, right? Now, so this comes out to be equal to RC by 2, or if you put R as RL by N or C as CL by N, so it becomes RC L square by 2. Okay? And if you remember the delay of, RC delay of a line, we say that the delay of a line is equal to RC. Okay? And yeah, so this is now RC by 2. Okay? And you will also find that here the delay is a quadratic function of the length. Yeah, delay increases as the quadratic function of length. Now, a distributed line can be represented by this symbol, right? So this is the symbol for. Can you please mute your mics? Please switch off your mics. Yeah, so a distributed line can be represented by this symbol, right? So this is lumped representation of a line, and this is a representation which says that this is distributed line, right? Now, if somebody asks me to find out, maybe let's say so somebody, maybe here itself, let's say that the current through this is I, okay, and this is, let's say, I2, and this is I3, right? So from here, let's try to find out Vi, that is at this node. Let's say this is I1, right? So let's say we have, the current equation goes like this, that is I1 which is going into this. So this is equal to I2 plus I3, right? So I1 is equal to I2 plus I3. So one can calculate I1 by simply saying I1 is, this node is Vi minus 1. So Vi minus 1 minus Vi by R delta L, right? So I1 can be written, I can write I1 as Vi minus 1 minus Vi divided by R delta L. Similarly, one can write I2, right? So I2 one can write as Vi minus Vi plus 1, Vi minus Vi plus 1 divide, no. Yeah, I2, correct. So this can be written as R delta L. So similarly, one can find out this one, I3. So I3 can be written as C delta L dvi by dt. Okay. So one can use this one, that is I1 is equal to I2 plus I3. Okay. And you arrive at this equation here, this one. Right. Now further, if you try to reduce this equation, you will arrive at this equation. Okay. Now for this equation, I mean this equation is different than the equation for the first order RC circuit. Okay. Now for this equation also we do not have any closed form a solution for this, right? Of course approximate solutions are present, but closed form solution does not exist. Okay, so that is why for finding out a delay of such kind of circuits where many time constants are there, one can utilize the Elmore delay model method. Okay. Now another important thing you will notice from this equation is that this equation is a popular equation, and this represents a diffusion equation. So what is diffusion here? Let us try to understand. So diffusion here means, in context of wire, it means that when a signal is coming from this node, that is input, a signal is coming from input, and then the same signal can be retrieved at this output node. Okay. So while undergoing through this wire, the signal value will also change depending on the length of the wire. That is, signal diffuses from this end. Whatever value, actual value was there at the input node, at the output, the signal, same value may not be obtained. Okay. So that is called actually diffusion. That is, input signal diffuses along the length of the wire. More the length of the wire is, more the signal at the output will be distorted and also attenuated. Okay. So that is, called diffusion here. Okay. So let us understand that by a simulation here. So this simulation is explaining us the step response of a RC wire as a function of time and space, right? So we have a long RC wire. Okay, so I have a length, some wire which has resistances and capacitances distributed across the length, and a step input is applied at the input over here, and along various sections of the length of the wire, that is L by 10. So if I have 10 sections, for example, so let us say this is my L by 10 section, this is my L by 9, L by 8, right, and so on. Okay. So that is, input signal is applied here when V in is applied here, and let's say this is my X is equal to L by 10. This is my X. Okay. So this is, let's say X is equal to L by 10 point. Okay. So at X is equal to L by 10, you observe a nice signal, good signal you observe here. Maybe whatever you apply at the input, so that you can observe at this point, L by 10. Okay. So depending upon again L, what is the length. Okay. So similarly, when you move further, maybe L by 4 point here, and then maybe L by 2 point here. So you will find that the signal, so that actually deteriorates or distorts or attenuates. So then similarly L by 2, so it further distorts, and then finally at the end X is equal to L, this point, so it further distorts, right? That is, signal actually diffuses, right? So it entered with a some strong value, some strong voltage level, but as the signal progresses along the length of the wire, the voltage levels at each point, so that is different from what you actually supplied at the input. So this is called diffusion here. Okay. And long wires, this problem you will observe mostly in the long wires. At the end of the wire, signal will be degraded, and this will represent in considerable delay. So for long wires, the delay will be more. That is, signal will also be distorted more. Okay. So that is how we say that driving these RC lines, that is long lines with R and C, and for minimizing delay and signal degradation. So these are one of the trickiest problem in DIC. So how to minimize delay of long RC wires and how to prevent signal degradation. So these are one of the trickiest problem in digital IC design. Now, based on our discussion, So let us again, redefine what we have studied. So we had seen lumped RC network and distributed RC network. Now for a lumped RC network, 50% delay can be calculated by using 0.69 RC formula. And for a distributed RC network, 50% delay is equal to 0.38 RC. So this difference you have to remember. For a lumped RC network, it is 0.69 RC, and distributed RC network, it is 0.38 RC. So distributed RC network is more accurate than the lumped RC network result. Okay. So more the number of sections are there on the wire, more accurate is the result. Similarly, 90%, that is 10 to 90% delay. So that is found by using this formula. We had seen 2.2 RC for a lumped RC network. For a distributed, it is 0.9 RC. So similarly, for a lumped RC network, for 63%, delay can also be calculated, and that comes out to be equal to RC. Okay. And for a distributed, it comes out to be equal to 0.5 RC. Okay. Now, these distributed and lumped networks can be either pi type or T type. Okay. So for example, here pi type networks are shown here, and here T type networks are shown. And the number of stages, that is how many sections are there. So this defines actually the accuracy of my distributed model. So let's say now that we are driving a RC line, okay, and let us say it's distributed. Let us say we are trying to drive a line which is a distributed line or a long length line. And let us say my driver has a series resistance of RS, and at the input I am applying V in. Okay. So now what would be the final delay at the output, right? So how do we calculate? So this can be calculated by again utilizing the same Elmore delay formula. And if you apply this Elmore delay formula, you will get delay as equal to RS times CW. Okay. Now CW is the total wire capacitance, okay, not the wire capacitance of each segment. Okay. It is total wire capacitance, right? And plus RWCW by 2. So RWCW by 2 we had seen that was the delay of distributed line. So I'll go back again. If you see here that RC by 2, yeah, this one. So this was the delay of a distributed line, RC by 2. So this comes up over here. The same delay, this is represented here, RWCW by 2 for a distributed line, right? Using Elmore delay formula. Okay. And then if you say that total capacitance for this line lumped value is CW, then due to this RS, you have this contribution. It is RS CW. Okay. So this comes up to be equal to now RS CW plus RCL by 2, right? Because R is RL by N, right? So R is RL by N and C is CL by N, small cl by N. So this comes out to be equal to 0.5 RWCWL square. Okay. And if you go by the lumped model and the distributed model, so if I say that this C is now lumped, so this becomes 0.69 RSCW because of lumped model, and because of distributed model for this, it becomes 0.38 RWCW. So two delay formulas can be arrived at. One is using the Elmore delay, and one is using both lumped and distributed approaches. So, yeah, so here both lumped and distributed approaches can be applied. So which gives me this result. And when you apply only Elmore delay model, then you get this delay, right? So two delays can be arrived at. Now this delay will be more accurate, yeah, this one. So this may be more accurate. Okay. So Elmore delay model may not be accurate, but yes, the distributed wire approach, this model can be more accurate.
Hello, sir.
Yeah, please.
The value of R is RL by N and C is CL by N. Where is the N square in the multiplication of RC by 2?
Yeah, correct. So let us go back again and check. Oh, sorry. So it was RCL square by 2 and n is large. So n is large, so it goes off. Right? So this becomes RC by 2 and R is RL by n, C is CL by n. So n is large. So in fact, you can put R here itself. R is RL by n and C is CL by n. N is large, so n goes off. So R becomes only R is RL now and C is CL. Okay? So when n is large, so n goes off. So R is now only RL and C is CL. Okay? So let us correct it here. So for long n, for large n, when n is large, okay? So when n is large, so R is only RL and C is only CL. Okay. Yeah, now let us talk about the design rules of thumb, right? So what could be the design rules for designing a interconnect or wire? Now the RC delays, it says rule number 1 is that RC delay should only be considered when the propagation delay of gate, the line is much greater than the propagation delay of gate, right? So RC delay should only be considered when propagation delay of the line is greater than the propagation delay of gate. So as I said already, I have I think answered this, that you're driving a line here, a distributed line, let's say. So when RC delay, this delay of line is greater than the delay of this inverter or gate. Okay? So then RC delay should be considered. Okay? Now this also defines a critical length, right? That is what length should be considered as, the length should be considered where, resistance should be brought in. Otherwise only capacitance only model can be considered for calculating the delay. Okay? But what would be the critical length when resistance cannot be ignored? Right? So that critical length, when the critical length is much greater than root of the propagation delay of gate divided by 0.38 RC, right? So I think somebody asked what critical length or what would be the length where the resistance will come into picture. So that number is actually this. Okay. So this depends again largely on this one, right? That is propagation delay of line is much greater than propagation delay of gate. So you will bring in the resistance also into picture for the wire. Okay. Now the other condition for critical length of the wire would be that critical length of the wire, if is much greater than this number, okay, then you will bring again the resistances into picture. Okay, because RC delay in that case will become dominant. Okay. So RC delay, or wire delay will become dominant. That is more greater than the propagation delay of the gate when the critical length, that is L, is greater than the critical length. So when L is greater than L critical, the RC delay of the wire will become now greater than the gate delay. So you will consider then in that case resistance also. Now next point says, next design rule of thumb says, RC delay should only be considered when the rise time at the line input is smaller than the RC delay. Okay, that is rise time at the line input, right? So I have some signal over here at the input which has some rise time and some fall time, right? So depending upon my rise time and fall time, I say whether my signal is fast or slow, or whether my signal is high frequency signal or a low frequency signal, depending upon the rise and fall times. Okay? And also the repetition frequency. Okay? So depending upon rise time, yeah. So if the rise time is large, okay? So let's say large rise time, maybe this much large, let's say. Okay? Rise time is very large, okay? And fall time is also large. Okay? Now in this case, the signal is very slow. Okay? And RC delay should only be considered when rise or fall time is smaller than the RC delay. That is this delay, that is rise time and fall delay is smaller than the delay of this one. So then in that case, the resistance of this thing should be considered. RC delay should be considered. Okay. So when the rise time, that is T rise, is less than RC, So then the resistance, this should be considered. Resistance of the wire should be considered. Now, what are the goals of wire engineering? So when we design a wire or interconnect, so what would be the goals? So the goals would again be the same. That is performance metrics for the gate. That is, you want to achieve a lower delay. You want to achieve a lower area for the interconnect wires. And also there may be power goals with acceptable noise, right? Then the degrees of freedom that are in the hands of designer, that is what designers can do to achieve these goals. So designers can play with width of the wire, the spacing between the wires, and the designers are permitted to play with the layers, that is metal layer process, maybe 5 metal layer or 6 metal layer process. And the designers can also use this logic, that is shielding a wire, two wires, by using a ground wire in between. For example, here a ground wire has been used in between these two wires. So this will act as a shield here, right? So these things can be done by the designer to achieve these goals. Then one can also think about using repeaters for long wires or long interconnects, yeah? Because we saw that when using long wires or long interconnects, because of that diffusion principle, that is signal diffuses as it moves along the length of the wire, so the final delay at the end would be very large. Okay, so that can be prevented, that is signal strength can be restored to the nominal values if I use repeaters in between the wire, right? So for example, the entire wire, I can divide this wire into number of sections, okay, and then these sections can be driven by the use of repeaters, right? So I can put in between repeaters. So the job of this repeaters or buffer is to restore the signal level. So because this is a long wire, so obviously the input level with the signal level which is applied here, so that may not be same when it reaches at this point. So to retain the actual input level at the output, one can think about inserting repeaters or buffer which will reinstate the value of the actual signal, right? So actual signal can now be present along all the sections of the wire. Okay. Now, how to decide how many number of repeaters, right? So how many number of repeaters, and what will be the at what frequency you will put in repeaters, right? That is how many repeaters and at what length the repeaters will be putting. So that can also be found. And in fact, let us read this point first. First, it says that R and C are proportional to L, right? Second point says RC delay is proportional to L square. We had already seen using Elmore delay model formula also that RC delay was proportional to L square. So RC delay will be unacceptably very large for long wires. For long wires, since the delay was increasing quadratically, so it will be unacceptably large for long wires. So that is why one has to think about breaking long wires into n shorter segments. Now, how many shorter segments? So that is again a problem here. So in this course, we'll understand. We will, when we cover our section on this CMOS inverters, we'll talk about how many, a number of shorter segments should be created on a long wire. So that, this n also depends, the number of inverters or buffer which we are using here. So this also depends upon the number of segments. Okay. Then drive each segment with the inverter or buffer so that the strength of the signal is same at each point, okay, along the wire. So that means I have to utilize this kind of model for the wire now, where wire will be divided into n number of sections and each section will have a length of L by n. Okay. and then each segment or each section can be driven by the repeaters or buffers, so that the signal strength remains same at the output of the wire. Yeah, so in the repeater design, we'll not study it now, we'll just see the formula, and we'll come on to how to calculate this formula later on when we talk about this CMOS inverter. But yes, let us say that in the repeater design, there are a few questions, that is how many repeaters should be used, and then how large each repeater should be. Okay? That is in this chain of repeaters which you are seeing. So it is possible to size these repeaters. I mean, this repeater can be bigger, okay? And maybe this can be a little bit smaller, and then this can be further more little small, then this can be further more little smaller, right? So this is called progressive sizing of the repeaters along the chain. So how to size these repeaters, this is also a part of this course. We'll understand how to size later on, right? So how large it should be, we'll see later. And then the equivalent circuit of these repeaters. Okay, so these equivalent circuit will obviously have NMOSes and PMOS. So sizing a repeater, yeah, so how large the repeater should be, that is sizing a repeater means we want to size the NMOS and PMOS which are inside these repeaters, right? So when you size NMOS or PMOS, then capacitance and resistance also scale. Okay? So that also we have to consider while designing or sizing a repeater. Now the optimum number of repeaters. So I'm straight away giving you formula here. We'll see later on how to derive this formula. Later on we'll see. But yes, let us digest at this moment that is total number of repeaters, that is optimum number of repeaters, can be given by this relation, that is L square root of 0.38 RC by the delay of this repeater, that is buffer delay or delay of this repeater. Okay. Then the optimum delay of this chain which has repeaters, right? That is this chain now which has repeaters. So optimum delay maybe at this point, let us say. So what would be the optimum delay at maybe this point? So that can also be calculated. Tau d, let's say. So this can be calculated by again using this relation, and how to arrive at this equation, again this is a part of this course. We'll study it later. But let us digest at this moment that the optimum delay in this case where you are using optimum number of repeaters would be equal to 2 times the square root of propagation delay of the unbuffered wire, that is wire which has no buffering, and the delay of wire with buffers. Okay. So the delay of wire with buffers and the delay of wire with no buffers. Okay. So these two things will be utilized to calculate the optimum propagation delay of this line which has buffers placed in between to keep the signal strength same at the output as the input. Now apart from these interconnects or wires which are actually used for point-to-point connection. Okay. So point-to-point connection again here means that you have two components which you are directly connecting by using a single wire, right? So this is called point-to-point connection. Now since there are trillions of devices now in integrated circuit, so this point-to-point connection of all these terminals or devices or nodes, so this is not a feasible solution. Okay. So you cannot think of using single wire for making connection between two ports. So in fact there must be some mechanism or theory by which one can utilize the same wire for driving many signals, right? Or what we call as concept of bus, right? So then apart from this point-to-point interconnects, you have bus-based interconnects. Okay? So where you have maybe some sort of 4 or 5 lines which you call as bus, and those 4 or 5 lines can drive maybe a number of signals, right? Maybe let's say 4 or 5 lines can drive, let's say 20 or 30 signals, right? So that can be thought
And
of. Yeah, I'm just finishing it. So point to point and then bus based. But again, you will find that bus based interconnect methodology. So this is also not a feasible solution. Okay. So one has to now think of some other solution apart from this point to point and bus based interconnect connection. So those could be one of them. The such sort of interconnect or wire connection could be based on this network on chip approach. Okay. So maybe I'll talk about this network on chip and this CNT based approach also in the next lecture. Okay. So if you have any queries, then maybe we can take up. Yeah, so if you have any queries, then you can ask. Otherwise, let us end the class.
Hello, sir.
Yeah, please.
Sir, I have some doubts regarding the assignment you provided us to do.
Okay, so
Can I ask you?
let us talk about the lecture first. If you have any queries about this lecture,
No,
then
I
maybe.
don't.
Okay, anybody else has some queries, then maybe we can take it here itself. And then we can talk about the assignment later. Okay, so I think that we don't have any queries. So let us talk about